In terms of natural resources, it is unlikely that the Earth can support an ever-growing population with progressively higher living standards forever. By giving man the necessary exploitation and transportation systems, he can make the entire solar system his raw material source and cultivate Earth as the biological center of a growing mankind. Initial studies of the first manned flights to Venus and Mars during the early 1970s have revealed the need for an ambitious program. History shows that such ambitions can be realized. The first age of discovery began when Henry the Navigator covered 1,200 miles between Portugal and the Azores. Only 90 years thereafter, Magellan had circled our world. Our present age of discovery began 4 centuries later. Now we have progressed to a point where we expect to reach the moon in this decade. Limited manned interplanetary flight can then come in the 70s. By the end of the 80s, we should have covered the entire solar system with instrumented probes. This then offers the realistic possibility that a Magellan could reach Pluto by 1995, just 53 years after the first large-scale rocket flight. This may be considered part of the answer to why we should now be preparing to develop manned interplanetary flight capability. Then come the questions: what do we want to do, how, and when? Our first objective is to demonstrate by actual accomplishment the feasibility of manned flights to Venus and Mars. We want to conduct low-altitude reconnaissance of these planets. In summary, we want to lay the foundations for the manned landing expeditions to follow. We have a choice of 3 mission types: flyby, where we simply make a hyperbolic encounter with the planet, pass through its activity sphere, and return to Earth; capture, where we stay near the planet as a satellite for anywhere from 10 to 50 days before returning. Detailed planetary reconnaissance involves many types of auxiliary vehicles. For example, for Mars we have studied mappers, floaters, landers, and returners, 2 of which also serve as Mars excursion vehicles for an optional, limited manned landing operation if judged feasible by the expedition. The Martian moons will be explored by separate probes. The third choice, of course, is surface landing involving a major assault on the planet with longer stay time and mobile exploratory capability. In terms of overall effort, the difference between flyby and capture is small. The same ships, the same unknowns, and the same risks are involved. Capture is somewhat more expensive, energy-wise, than flyby, but yields the greatest return in terms of information and progress toward a major landing mission, which must be the ultimate objective. The life support system, protected by 11,500 pounds of polyethylene shielding, is highly modularized. Here we have 4 mission modules containing 4 2-man rooms, an observatory, food, sanitation and storage facilities, a gymnasium, a scientific and medical lab, library and recreation area, and a repair shop. The heart of the life support system, the command module, is immersed in the Maneuver 4 hydrogen tank. Containing all control and other key equipment, it also serves as a radiation storm shelter for the entire crew by virtue of combined polyethylene and hydrogen shielding. A utility shaft with a system of airlocks provides access to the mission modules, 2 space taxis which are used for intervehicle travel and module exchange operations, and to the 8-man Apollo-type Earth entry module. Front sections of the service vehicles carry auxiliary vehicles of comparable weight. Only one accompanies the cruise ship back to Earth. Now it has almost no payload but enough propellant to carry the crew and its life support system during the target planet escape and Earth capture maneuvers in case the original crew vehicle is incapacitated. The life support system, except the Earth entry module, is jettisoned prior to Earth capture. The orbital energy of the cruise ship is then reduced to a slightly negative value to retain Earth capture, giving expected Apollo conditions for atmospheric entry. This is the weight distribution of a self-sufficient crew vehicle for a typical reference mission to Mars in 1973.